Swayam Prabha. Digital India. Educated India.
This is kinematics of rigid body. Kinematics, of course, you understand, it's a analysis of motion, study of motion, without recourse to what caused the motion, without recourse to forces. So essentially, it is a rigid body which we need to understand. What are the, how we describe rigid body, what are the implications when we mean by rigid body. Rigid bodies come under the class of solids, as against liquids. And the solids, of course, you know, it's the way assume that it is consisting of a number of particles, a system of particles. And as a solid body, we say that the particles keep their neighborhood, in the sense that even under deformation, the neighboring particles remain neighbors. So that's what a solid is. So solids are classified into rigid body and deformable bodies. In rigid body, the distances between particles remain unchanged during the course of motion. On the other hand, the deformable bodies, the neighboring particles remain neighbor, but the distances between them may change. So under deformation, like deformation may be of many, you know very well that if a rod is subjected to a forces, say inline forces, so then we say that the deformation may take place, which we call as a strain. So it will undergo strain under the application of force, maybe which can be said stress, force divided by area. So the deformation there are of microns, so 10 to the power of -6. That is the order of deformation in a deformable steel or elastically deformable material, steel, aluminum, concrete. The deformation is of the order of 10 to the power of -6, maybe at the best -5. So that we neglect for two reasons. One reason is that we are not actually doing the deformation, elastically deformations on one hand. On the other hand, even when there are a lot of deformation that's there, we might neglect it in comparison to the larger motions. For example, if the example which they say is that which is in motion or long distances, maybe Delhi to London or something, 5,000 kilometers, in which we also see that there is a deformation of wings. So if you sit in a plane, you might see the wing almost deforms by, the wing tip almost deforms by half a meter. Okay, it vibrates by half a meter. The wing is very long, right? 10 meters, 15 meters long. So wing tip almost goes through a deformation of half a meter to 1 meter. But that is it big or is it small? So that is in comparison with something else. Always, as I keep telling, something is small or big is in comparison to something else. So that deformation can be neglected in comparison to the overall motion of the plane while going from Delhi to London or anything like that. But that deformation is not negligible when you talk about the stresses and strains that are produced within the body, or when you consider the vibration. Okay. So as far as our definition of rigid body is concerned, we neglect those deformations because because we are talking about the motion of the body as a whole over much larger distance. Okay, so that is why we consider all the bodies here as rigid body as far as present study is concerned. Not that our bodies do not deform. Only thing is that the deformations are very small compared to the overall motion parameters. So, all right. So, this lower figure here talks about 1D motion, 2D motion, and 3D motion. So, what do we mean by 1D motion? So, here, all the particles are moving in x direction, and the body remains parallel to itself while undergoing the motion, in the sense that the path of the particles are straight lines parallel to each other. So all parallel to, let us say here, x-axis. So this is a really one-dimensional body, and we consider that it has a degree of freedom 1. While it is that's simple, we have done a number of times. So may even be curvilinear. I'll talk about that a little bit later. So there is a two-dimensional motion in which the planes, so which I showed it in hash. So those planes, for example, remain parallel. So that means that as it goes from one position to another position, that plane is moving in the same plane, let us say xy. So it is neither going up or down. So all the particles, but however, we say that all the particles in that plane will be moving in the xy, okay, with the restriction of rigid body. And the important thing here is that any particle in the parallel planes continue to have their own parallel plane motion. So this means that any motion here of the particle is either in, say, xy plane or any xy plane parallel to this. Okay, it is less like slices. You assume that it is in the form of slices you cut in a horizontal plane, and every particle will move in its own horizontal plane, in its own horizontal plane. So that way, what we require here is only the analysis of 2D motion. So every particle is moving either in xy or parallel to xy plane itself. That is 2D. We consider this 2D in detail in the due course. Even today, we'll see quite a bit of that. Okay, and then the 3D obviously is a very general motion, and the body can move, rotate in all the 3 planes. So that is the most general. Okay. So now let us look at a little bit more into detail. 1D motion is very simple. Let's consider the 2D motion. Yeah, you can all hear me and see this slide, right? Everybody can see this slide? Yeah, okay. So this is a slide which just gives you some more figures, and we'll go into the details of this plane motion in 2D. In 2D, it can be classified as some simple translation. So as I said, that each slice of the body is moving in xy plane or parallel to xy plane itself. And here in the translation, so you can see here, interestingly, in the translation, what happens is that the orientation of the body remains parallel, but however, each particle will execute a certain path. So the top one is going from A1 to A2 in straight line. And in translation, so all the other particles kind of parallel. We can't say parallel, but congruent paths. So the top one, if it is rectilinear translation, so the body remains parallel to itself and keeps moving. Whereas the second one is again here, body remains parallel to itself during motion, but however, each particle executes a curved path. So you can see that this A1 here is taking a path like this, and B1 is also taking a path congruent to this one. Okay, so that means that anywhere, wherever the body is, so the distance between them remains constant. So here the path is curvilinear. So there are two translations, curvilinear. So one of the things, example here, is that there is a slab here, the rectangular plate, which is constrained to move by hinging it at these 2 points by two rods of equal length. So the motion is on such a manner that, say, you can see that this dotted line A1, B1, C1, D1, that is the original position. And during the motion, it occupies A2, B2, D2, C2. So you can see that this motion is such that the body is maintaining its own original orientation. Orientation is not changing. But however, each particle here, each particle here is executing a circular motion. So you can say curve. So it's circular curve. So the interesting thing here is that though you think that maybe the orientation may be changing, but it's not. It's always the body is keeping itself same orientation. And however, each point here can move along a curved path. So whereas here, this is the another part of the plane motion. The first one is translation, rectilinear or curvilinear. Another is rotation. So here, the body is big. I mean, don't think that it is a very thin like paper or even a small slab. But only thing is that here you can see that there is one line here which is fixed, which is, that means the particle on this line are not moving at all. And every particle is moving in a circular path. So the rigid body is going to have a circular motion. Orientate, I mean, it's having an angular rotation about this axis. So this is the axis here. So you can see very well that each particle is having a circular motion in a plane which is perpendicular to the axis. So that means that all these motions of the particles are in parallel plane in circular paths whose center is on this axis. Okay. So you can even say that, well, you can collapse them along this axis. For example, if you consider this is the axis, say Z axis, if you project the whole body, then it will look like this one. So the XY plane and this O here is a point, but in actuality, it is a line. It's an axis perpendicular to the plane of the paper here. So then each particle here is executing a motion in the XY plane. So here each, you can see that this A2 is moving in this circle and this C2 is moving on a bigger circle. So this is a simple rotation. So there are, the plane motion consists of either divided into a pure translation or pure rotation. But a general plane motion is a combination of these two. A general plane motion. So that means, for example, I'm going to explain it to you a little bit more in detail. So for example, if there is a wheel rolling, so then obviously the center point is kind of having a translation that you can see, okay, while every other point here is not only translating, but also rotating. So, okay, a point here on the top, for example, will go to some position later, maybe after 30, 45 degrees along this one. So that means that the particle is having a general motion. We are going to see a little bit more in detail. So similarly here. So here, this is the most often taken example, a rod going along horizontal line and along a vertical guide. So this is also is a general plane motion. So we'll go a little bit into detail now. These are some more examples here. So what is rectilinear translation. This is which we discussed in just in the previous slide. So here, this is a general body written, not as a rectangular slab or anything like that. So a general body which is keeping same orientation. So AB is keeping the same orientation and it's moving. So this is a rectilinear translation. Every path is rectilinear. And then this is every particle is executing a curved path. So, but however, the orientation remains same. And this is the example which we have taken. So this is a curvilinear translation. And the top one is really a rectilinear translation. And which we can even construe that it is a 1D motion, right? So every particle here is having a motion in x direction only. Then other example we have seen is a rotation. So if you can see that any line drawn here, the radial line which is drawn from A to B will remain radial, and then every particle here is executing a circular arc. So this is a kind of pendulum. And then these are general motion. So this is actually we are concerned. We are concerned about the general plane motion. These are the simple. Only certain few cases, it will be either pure translation or a pure rotation. But on the other hand, here, for example, so in this example of a crank and a connecting rod and a piston, this crank is having a rotation about this point, whereas this piston is having a rectilinear translation, while the connecting rod here is neither pure translation or a pure rotation. Okay, so that way this is having general motion, whereas this is having a rotation and this is having a translation. So let us just say a little bit more in. We'll come back to the 2D, but I'll just try to see one more, which we are going to see much later, which is a little bit complex. So in three-dimensional motion, for example, this is a top, which you are aware, and which is really a 3D motion. So because it is spinning about its own axis, as well as it is precessing about a vertical axis here. So you know very well. So here, it's not a plane motion. It is a fully three-dimensional motion. Every particle is having a 3D motion, and they're neither parallel or translational or pure translation. This is but however, one classification, one thing which we can say is that it is at least one point in the body is remaining fixed. So it is stationary. And all the other points are having some or other complex motion. So, and there's no question of translation. So translation is truly very trivial here, which you can even say it's a plane. Okay, planar translation, similar to planar translation. So in the sense that if the body is keeping its own orientation, and then, but however, if it is having a translational in 3-dimensional, it is possible, but keeping the same orientation. So these are general 3-dimensional motions. You can see here, so similar to this example, we have a here disk rotating about this point, as well as this arm here on which this point A is. So that is rotating with a certain angular motion about the vertical axis. So that way, this disk is having a 3-dimensional motion. And so similarly here, this is a bullet, and bullet for some reason is given a high spin about its own axis, but because of some wind and so on, so it is going to persist about some other axis. So this is also 3D. Of course, you can very well appreciate this one. This is some robo, and in which it's a complex motion. Say, for example, this rod here, which this robo is gripping, is going to have a complete 3-dimensional motion, because a rotation is given about this, a rotation is given about this, and another rotation omega-4, omega-3, and omega-5. So there's so many. So you can really see that this is a very complicated complex motion. So finally our interest is to go to this one. Okay, at the end of the probably at the end of the this course, maybe you may be able to touch upon the analysis. So what if you see the next one? So why we are interested in translation and rotation? It is because any general motion can be construed as consisting of a translation and rotation. So it can be divided into a translation plus a rotation. A combination of these two will be able to model any motion. General motion means any motion. For example, in this a disk rolling on a ground, you can see very well that this line A1, B1 after rolling will occupy this A2, B2. And so obviously A1 is having this kind of motion, B1 is also having some other kind of B1. If you see, is going to have a cycloidal profile, you remember, while A1 is having a rectilinear profile. And so this can be construed as a pure translation. So assume that the whole disk is sliding, okay? Forget about the friction and so on. And it is just sliding from this position to this position without any change in the orientation. So A1, B1 remain parallel to A2, B1 prime. And this is called, you very well see, since the orientation is not changing, it's a pure translation. On the other hand, after having come here, okay, come to the next one, we can assume that this is having an angular displacement. This is having an angular displacement. So a translational thing followed by having come here, then a rotation. So you might ask, sir, is it really doing it in steps? So is it first translation and followed by rotation? No, it's not necessary. It's not necessary. All these two things can work simultaneously. You can even say that this is delta x and delta theta. So delta x and delta theta can be very small, so almost occurring simultaneously. So similarly here, this rod here, A1, B1, which was like this, which is going to occupy a position A2, B2 later, can be construed as a translation, okay, the rod remaining parallel to itself, and then having come here, then you rotate it counterclockwise by a small angle here, so that this constrained motion of B, it's supposed to move only in the vertical direction, right? So you bring it back to the vertical line. That's what the final position will be. So here also you can see that a translational plus rotation. So this is a very, very general rule. So that means that any general plane motion can be construed as having a translational and rotational, okay, in small. If it's a continuous motion, so you can say it is delta x followed by delta theta, and almost occurring simultaneously. So this is, we can say here, a general thing. So if you have a general shaped body, so you can say that this is A1, B1, and it has taken this position while A2, B2 is like. So here also, as just now we said, so it is having a translation. So A1, B1, A1 is coming to the final position A2, B1 is occupying some other intermediate position, and B1 is rotated to the final position. So this is the very important for us for our analysis. Whole of our analysis is based on this one, all our analysis. So we say that general motion is going to consist of a translational and a rotation. Okay. And now let's look at, in summary, this is very important for us. In summary, what we say is a rigid body in plane motion. Now we are introducing degrees of freedom. Now we have been talking about this a lot. So since now that we have agreed that the general plane motion can be consisting of a translational and rotational, then we can say that if you think that it is moving along with A, so the point A can be construed as having two displacements in X and Y respectively, and then followed by a rotation about Z axis. So this is very important for us. So that means that any displacement can be of any point. It's not necessary only for A1 and B1. It is, if these three are given, you can find out the displacement of any other point, not only B, it may be even C. So the first two, the displacements of a point obviously are, you should know, they are functions of time. So they may vary from another one point to another point. And however, interestingly, the rotation part does not depend upon the position of A1, B1. I mean, if you say that here, I'll go back here. So here, the interesting part here is that this is the translational part. And so obviously, this much of translation depends upon whether you take A, okay, and then taking B1, rotating about A1. So what reference point you take to talk about the translation obviously is going to decide your translational components. While the rotation part here, this is the interesting point. So the rotation part here by a certain delta theta is same for any line, whether you take A1, B1 like this or A1, B1 like this at some other angle. And then you calculate B1, the new position of B1 here. So if you take another here, point some other location here for A1, obviously it is translational components will change. But however, the orientation, the delta theta of any line is same. So this is the interesting point. Of course, you can realize that the translational is components are of a point, whereas the rotation is of a line. And so the rotation of any line is same, whether you take it as A1, B1 or maybe C1, D1, the rotation is exactly the same. So it will not change. Okay. Interestingly, we'll talk about this later. So if I go back here, yeah, interestingly, you can even think about this one. Here we are talking about it is translating with A and the body is rotating about A. So it's translational, two components, and rotation about A. So you can even say similarly, it's if you take B1, so you can say that it is B1 to B2, it is translating, and about B2, A is rotating. Okay. The interesting part is that whether you take A as the reference point and B is rotating about A, or if you take B as a reference point and A is rotating, so you will get the same. And interesting point here is that the rotation is the same. Okay. So this is what it is. So that way you can now appreciate that a body in 2D plane motion has 3 degrees of freedom. So that means that if you give the displacements of a point in X and Y direction and rotation of any line, in fact, any line will have the same rotation if you give the rotation. So that you can determine the new position of any point. Okay. So this is what I wrote here. This essentially means that the displacement of any point can be found if we know the displacement of any other point and angular displacement of the rigid body. Okay. And so in 2D, so we are going to use this concept that it is going to have 3 degrees of freedom. And so that means that again, I'm emphasizing is now the rigid body is supposed to consisting of infinite number of points. So that means that if you know any point translational components and the rotation, you can find out the displacement of any other point. So they're all fixed. So they are no more independent. If you know these three, you can find out the displacement of any other point. So similarly, we will see this later, is that a rigid body in three-dimensional motion has 6 degrees of freedom. We can very easily extend this one. So almost the same concept. Translational motion of a point and rotation about that point. So the translation of a point has 3 degrees of freedom, right? X, Y, Z displacement components. And the rotation has 3 components. So again, about x-axis, about y-axis, about z-axis. So thus you have 6 degrees of freedom. So like this, so this is, I hope you have appreciated that what is the difference between one-dimensional motion, two-dimensional motion, and three-dimensional motion of a rigid body. In one-dimensional motion, it has got only 1 degree of freedom. The body does not change its orientation. It is the whole body is moving parallel to itself along x-axis, nothing else. Whereas in two-dimensional motion, the body, if you consider to be a slab or a projected onto xy plane, so it is going to have an xy plane motion, which can be totally described by knowing the position of a point and the rotation of the body of any line. So that is 3 degrees of freedom. And this can be extended to 3 dimensions, where you can find out the position of any point in the body if you know the position of another point and the rotational component. Okay. So what is that finally which we have to do? So we have to go step by step. So we'll analyze the two-dimensional motion. The two-dimensional motion, I said that it is divided into 2 components, a translational and rotation. So the analysis of translation and rotation are different, simple though. And we say that the final general plane motion is a sum of these two, obviously vector sum. For example, in this top portion here, the translation analysis is very simple. Either it can be like this one, rectilinear translation, so wherein the orientation is all remaining same, A, B, A prime, B prime, A double prime, B prime. On the other hand, I even said that you can even take any other line, AC here, and A prime, C prime. So they also remain parallel to themselves and keep moving. Okay. So that means that if you know the path of one particle, all other parts are congruent to that. Okay. All other parts. For example, if you know the position of, if you know the path of this one, you can find out the velocity of point A at this point. So since these paths are all parallel to themselves, congruent, so the all other points here will also have the same velocity. So that's what I think I wrote here. This is rectilinear and this is curvilinear translation. Again, the orientations remain same of each line, and the paths are of each point is congruent. So if you know the path of A, you know the path of B also. Okay. So finally the sum is that, so if you know the velocity of A, the velocity of B is the same. So okay. And if you know the acceleration of B, so if you know acceleration of A, you can find out the acceleration of B, it is the same. So this is the property of the translation. Okay. And then the rotation part here is, we know that it is about a fixed line. So that's what the 2D motion. But however, if you project them on a plane perpendicular to the axis, I'll just go to the next one. Yeah, I think, yeah. So please see this one. Here I tried to show that any radial line will be moving by an angle of theta. And even if they are not radial lines, they also will undergo the same rotation. And so if you see the rotation part, the projected into xy plane. So a general body here, AB will go through A prime, B prime. Okay, that's what it is. So if we have done this a lot while doing the particle motion, particle moving around, particle moving about another point, another axis. Here we call it axis. So here A is fixed, and then B is moving in a plane perpendicular to the axis, and obviously passing through the point. So here a little bit of simple vectorial analysis, very simple, is here. We have seen that in a infinitesimal displacement motion, so A is fixed and B is going to be prime, and going through an angle of d theta, and R is taking position of R prime, and this delta R is the displacement. So delta R is R prime minus R, and we have done this analysis, so that's why I'm just doing this quickly. So the magnitude of this vector BB prime in the limit is nothing but R delta theta. What about the direction of delta R? So delta R in the limit is perpendicular to AB. So if you can draw a line here, so this phi becomes 90 degrees. So in the limit. So the delta R can be written as delta theta times R. Okay, that's that part. And K, sorry, this is not delta R, it is R. Okay, delta theta K cross R. And this is what we have done in the beginning also. So this is about delta R. So you can take divided by delta T as a quotient. So that becomes a velocity, and delta theta by delta T becomes omega, and K cross R. So in the vectorial form, so that gives the direction of delta R, and we can write omega K cross R. So thus we can write it either omega K cross R, or if you give omega K itself, if you think that it's omega vector, so we can say that omega cross R. So that's also is possible. So coming to the next part, the acceleration. So if you want to differentiate this one, if you want to differentiate velocity, so it's omega R dot, omega cross R dot plus omega dot R. So this is simple here. Omega dot is nothing but the acceleration alpha. And since omega is not changing in the sense that omega direction is not changing, only the magnitude is changing. So the d omega by dt times k. So it's only change in the magnitude. So we can still say alpha k. And this omega r dot continues to be omega cross v. So interestingly, this is v, you can replace it by omega cross r. So it is omega cross r, and this is alpha cross r. So what are these two components? So you can see that this is alpha cross r similar to omega cross r. So it is in the, if you think that this is A, this is B, so omega cross r is nothing but tangential direction. So it's perpendicular to the radial line and in the tangential direction. So you can very easily see. So the first component here, omega cross r. So you know how to take this triple product. So this is velocity, which is in this direction, and we have to take a cross product with omega. So omega cross v. So you know very well omega cross v. So if you apply a right hand screw rule, so then it will be pointed in this direction. Okay, so this we call as normal acceleration, or maybe you can even call it as a radial acceleration. So what is since all these things vectors are perpendicular to each other, so the magnitude of that is only omega square r. Okay, magnitude of that is only omega square r, and you can see the direction is nothing but from here to towards the center. So this is radially inward. So we know what are these meanings are. So this is the tangential acceleration, and this is the radial acceleration or centripetal acceleration. So that way, so interestingly, we have translational thing and we have rotational thing. So this is translational and rotational dealt separately. And we can even combine them. For example, we can say that AB is equal to AA, or say VB. VB is equal to VA. That's the translation part, plus omega cross R. So that will give you what is R. R is assuming that the body B is rotating, point B is rotating about A. So that is the vector R, and omega is the angular velocity. So thus we have analyzed the translational component and rotational component separately. And now we can get into the analysis of motion. And so there are two approaches. So here, two approaches are, this is a simple approach, direct analytical approach, where if you can give the expression for x of a point you are interested in as a function of time, maybe in any way, then you can differentiate it to get velocity. You can differentiate it further to get the acceleration. So these examples are when the writing down the position of any point as a function of time in a simple terms. Whereas we have a much general approach, that's the relative motion component, which we are going to see. That's done more. So here in this simple example of a disk rolling on horizontal ground, quick one, is that there is the original position and this is the position after some time. So for example, this OC is occupying O prime, C prime. So O is moving by a certain distance, and while because of the rolling, so C, which was originally bottom down here, has moved through C prime by an angle of theta. So you can very well see that that since it's rolling without any slippage, so this AC prime is supposed to be equal to OO prime. So we can say that the distance traveled S is equal to R times theta. So this is the distance traveled is S, and that is the arc length here, and it's related to theta as R theta. So this is a very simple analysis here, very simple, amenable to this set of equations. So you can differentiate it to get velocity, V is equal to R omega. We can also differentiate it once more to get acceleration of R alpha of any point C here. Okay. So this is, this is how these are related. So this is given for the bottom point C. So using that, we can derive this one. So I think I'll stop here and we'll continue this our class in the next on Monday.